Hey everybody, welcome back to Spatial. So last time we finished on, I believe, this slide here where we were trying to compute the Morenzai statistic, which is essentially a measure of spatial autocorrelation, how much of the information is shared on average between first order, second order, third order neighbors. And we made a conjecture that because gonorrhea and HIV have similarities in terms of their method of transmission, they're both STDs, they would have similar autocorrelation patterns. In fact, they're high in relatively similar areas of New York City. And then for comparison's sake, I put in this no health insurance under 18 example to be something pretty different. And although we detected, statistically significant, technically, autocorrelation, the autocorrelation is far weaker than the other two. So the Morenzai, the global Morenzai, assumes the same, stationarity. Global Morenzai assumes stationarity, that the nature of spatial autocorrelation is sort of the same across the entire region. Dr. Luke Anselin in 1995, which was pretty recent on the scale of statistics, the global Morenzai was in the 1950s, thought of the local Morenzai. So it basically takes the global version of the statistic and does this for each region's individual neighborhood. So there are as many Morenzai statistics as there are neighborhoods. So basically one statistic, autocorrelation statistic per neighborhood area. And it's used in exploratory methods to identify spatial outliers and to identify clusters. So there are 4 different types of local Morenzai. The high among high, so an area with a high value among other areas with high values. Low among low, the inverse of number 1. High among low is an example of one of those spatial outliers. If you have an area with a high anything among other regions with low something, you're going to have a spatial outlier, and of course, low among high. So remember, in the numerator of the Morenzai, we actually have a covariance. This is a covariance. And the local Morenzai just includes only those areas that border each region into the computation. So in the case of 1 and 2, high among high and low among low, we're talking about a similarity, right? It's positive autocorrelation, and so the I statistic is positive. In the case of spatial outliers, 3 and 4, we have a high among low, low among high, that one is not like the others, and so the I statistic is negative. And again, just to be clear, notice the fact that I put a subscript. It's the Morenzai for the ith region, not the global one. Now, the issue is, like the global value, we can test each statistic. Each statistic is a valid statistic. You can assume the null hypothesis of independence, and you can perform a hypothesis test. However, because you have as many statistics and p-values as you do regions, you have to adjust p-values for multiple comparison. I'm hoping you guys have heard of multiple comparison adjustments before. And this happens when you are comparing, for example, a lot of different averages or a lot of different proportions. In order to control type 1 error rate correctly, you have to adjust those p-values. You have to, for example, using the Bonferroni method, if you're comparing, say, k things, in the Bonferroni method, you compare your p-value not to alpha, but to the alpha to the power of 1 over k. So unadjusted p-values are going to have inflated type 1 error rate. You're going to, in this case, you're going to detect too many regions of interest. So there are several ways of adjusting the p-value. In fact, there are whole short courses offered on how to adjust these p-values. My recommendation, we're still in this case talking about an exploratory data analysis. Go ahead and just use the most conservative one. You will detect the fewest number of regions of interest using the Bonferroni. It's the most conservative one. It will detect the fewest number of regions, but you won't be sort of pulled in an incorrect direction with your exploratory analysis. It's always good to be conservative during exploratory analysis. And so how does it work? Well, you know, the code isn't particularly complicated. You have your outcome variable. You guys have seen this, neighborhood to a list using binary queen adjacency. And then it produces basically a matrix, has as many rows as there are a number of regions. So here is the I statistic for each region, its expected value under the null, its variance under the null, which we can then use together to find a z-score. So notice we don't adjust the z-score. The z-score is what it is. It is you know, simply the ratio of the test statistic minus the expectation under the null over the variance. I'm sorry, over the standard deviation, not the variance. So we don't adjust the z-score. You can still say that, hey, there's, you know, this is elevated Moran's I statistic and it's positive. But if you look at what that p-value produces, and these are adjusted p-values, these are Bonferroni adjusted p-values, this is 0.22, this first p-value right here. So although without adjusting, a z-score of 1.85 would have a p-value of somewhere like 0.06, 0.07, because we have used an adjustment method, our p-values have grown a little bit. So you can see several of these p-values are just 1 exactly, and a few of these are essentially 0. Now, with a little bit of programming, and in a software like ArcGIS, this will be done automatically, but we're not using ArcGIS, we're using R, and this is code that I have available. You can simply classify the significance and the value of the test statistic into one of the 4 clusters: high among high, low among low, high among low, low among high. And what people do is they either plot the p-value itself, and by the way, I just want to point out that using an unadjusted p-value, like I do on the right, you can see that we detect more clusters. There is more that is detected, and you know, although on my map it's missing, it's just not significant. But because we detect more things, some of those are false positives because we're not controlling for the type 1 error rate correctly. Bonferroni is the most conservative. That's why we, you know, detect the fewest number of these things. So sometimes you will see maps of the p-value plotted, and you can see all these ones. This brown color right here are all the ones with a p-value exactly 1. You will notice what the adjustment has done between the 2 maps. But then you do see a few of these that do have statistically significant p-values, and those are the really light colors, right? Even something like this orange color is not significant enough. So if we actually just plot those clusters that are significant, we see what's going on. So we have a high cluster as this greenish color here, here, and here, and we have a low cluster as this yellowish color there. And of course, on the right, we have detected more and more things. So this sort of concludes the exploratory data analysis portion, and we can sort of move into the modeling. I always, always, always recommend that you perform some type of exploratory data analysis first so that you can sort of have a BS detector when you're performing the modeling. plot the data, perform some type of exploratory data analysis. And this could be as simple as just map the rates. Map the rates. So that, when you're looking at the model, you sort of have a sense of what to expect. So with that, let's move into the last set of notes of the semester. Very, very exciting. And we'll be talking about models that are called conditional autoregressive models. And these are difficult to do internet searches on because these spell out CAR or CAR. And if you just search for CAR models, you can imagine what you find. So the way you search for the internet, on the internet for these is to go spatial CAR, and that usually does the trick. I want to go back to a key player in the next couple of slides, a few slides, a lot of the slides, is our adjacency matrix. It encodes or records the neighborhood structure using ones and zeros, where the ones are the neighbors and the zeros are not the neighbors. So for example, here's the 48 continental US states. And last time we did a little bit of looking that Maine, for example, has just one neighbor. This is Maine. And Wyoming, our good old state of Wyoming, has 6. You can actually count them. And there's 6 here. 3, 4, 5, and 6. And there are 6 because we have 1, 2, 3, 4, 5, and 6. All right. So this, we will have our adjacency matrix play kind of a key role and really a similar role to which the distance matrix plays inside of the geostatistical model. So a slide coming up with some notation, but I am specifically trying to show that there's not that much of a difference between our geostatistical models that we've gone over before and the new material, which are the areal data analysis models. So the geostatistical models we have here is the marginal ones, marginal models. So here is the mean function right here. And then this should look familiar to you guys, right? This is the spatial variance, correlation matrix. Here is the nugget effect that you guys incorporated with your homework. We can write this marginal model in its conditional form. And it's conditional because this specifies the distribution of our outcome conditional on our latent spatial effects. And then on this top level, we basically have an independent normal model. On the bottom level, all the spatial correlation is encoded right there. And again, this blue H is reminding us all the places that the distance matrix appears. And this distance matrix, of course, encodes similarity in location as a function of your latitudes and longitudes, eastings and northings. Now, we haven't done this, but it's not particularly crazy to take a conditional type of specification and feed it in a transformed format like this into a different distribution than a normal. For example, it's very common. On this level, you fit your spatial model and you specify your may turn, you specify your spherical. Notice no nugget effect, right? There's no nugget effect there. And then you specify a Poisson that is conditional on these omegas. And you sort of just add them into the mean function. You essentially smooth out the means of the Poisson distribution. Now, here on the right, there is a lot of very similar notation because it is similar. Our spatial latent effects are also going to come from a multivariate normal distribution, and it is also going to have a zero mean. The difference is in the variance covariance matrix. So this is the conditional autoregressive variance covariance matrix. This thing, it's great. Only a couple of days left. So look, Our variance covariance matrix for the conditional autoregressive model includes the adjacency matrix. Our variance covariance matrix for the geostatistical model includes the distance matrix, because it again encodes how similar in the location, similarity in location between observations. The omegas are the latent spatial effects, latent because they're unmeasured. And guess what? On the right, it's exactly the same thing. So one way to think about it is that these are a linear combination of everything that is spatially structured that is not in the model. And we can actually interpret these. They're going to be spatially correlated. So, and they will reflect linear combination of all the covariates that matter. It's not noise. Noise is uncorrelated. Residuals are outside of this. Residuals are what is left over after you account for the spatial correlation. So these omegas are not residuals. They're not noise. They're spatially structured components of the model that are latent, they're unmeasured, and they reflect a linear combination of everything that is not in the model. On the left-hand side, the theta is the range parameter, right? It controls how quickly correlation decays as a function of distance. On the right, the rho is called a smoothing parameter. And in the literature, this can be a lot of different Greek letters. But you know what it's not? It is not a correlation. Even if it's a number between 0 and 1, even if it's a number between -1 and 1, this rho inside of a conditional autoregressive spatial model is not a correlation. It is a spatial smoothing parameter, right? Correlations are interpreted a certain way, and we will soon see how to interpret this spatial smoothing parameter, but it is not a correlation. We really want it to be a correlation to interpret it that way, but it is just not. And W, of course, is the adjacency matrix. So I made this slide not to scare you with crazy Greek notation, but just to draw all the different parallels from the beginning of the course when we dealt with geostatistical models to the end of the course when we're dealing with areal models. The only really big thing that changed is how we are encoding how far apart our observations are. Okay, I think I've said a lot of this already, but our adjacency matrix is an n by n matrix, zeros on the diagonal. Sometimes it's called a weight matrix. It weights your neighbors with a weight of 1, and it weights everything that is not a neighbor with a weight of 0. The diagonals have zeros on them. This too is very similar to a distance matrix. Regions are not their own neighbors. We will be talking about, there are a few CAR models out there, but the most common one, or very common one, is called a proper CAR model or a classic CAR model. Try Googling classic CAR models, see what comes up in your Google search. It dates back to the 70s, particularly popularized by Noel Cressy in the early 90s when he released sort of the super famous spatial statistics textbook. So here is the specification that you guys already know. W is the adjacency matrix. This capital D is a diagonal matrix, n by n diagonal matrix with the number of neighbors on the diagonal. So not to be confused with the identity matrix, which just has ones in the diagonal. This matrix is n by n with the number of neighbors that each region has on the diagonal. Of course, here is the spatial variance. And I'm specifically using the spatial variance because the nugget term, error variance, is introduced at the top level after we account for the spatial latent effects. And this is true for both models. Other distributions don't have an error variance at all, right? The Poisson distribution doesn't have an error term, it just has the mean. The Bernoulli distribution, binomial distribution, don't have a nugget variance at all. So it's appropriate to use this spatial variance notation we've been using of alpha squared. Now, in this class, we're sort of bound by frequentist statistics because a lot of this stuff, a lot of the models for areal data happen in a Bayesian context. And if you have that background, for example, if you're in my Bayesian class, there is a pretty good package that has a lot more options than what we will have available to us. We'll be using a package that has one type of CAR model. The package that we'll be using is called SPA-MM, and it has only one type of CAR model. Again, this one here has many other options, but it is in a Bayesian paradigm, and so we will not be covering it here because this is in our spatial stats class, we are frequentists. In my Bayesian class, we are Bayesians. So here's the most common variation. And in the literature, you will see this written a few different kinds of ways. This notation that includes the multivariate normal, right? This is n-dimensional, implies this conditional distribution for each location given its neighborhood. So once we identify a neighborhood structure with our adjacency matrix, we give this model its neighborhood. So conditional on the neighbors, we have an independent normal distribution where the mean for the ith region is the average value in the neighborhood. Weighted by the smoothing parameter rho. So we want to induce spatial correlation. For every region, we look at the neighbors. Then we take the average of those neighbors, we put it inside of the mean of a normal distribution, weigh that mean, multiply that mean by the smoothing parameter, which can be between 0 and 1, by the way. And the variance is alpha squared, which is our spatial variance, divided by n, which is the number of neighbors for our region. So that's sort of a relatively intuitive way to ensure that you have a smooth surface. Smooth surfaces exhibit a large amount of positive spatial correlation. If you take my value to be the average of my neighborhood, you are inducing spatial correlation. So what happens when a region has few neighbors? For example, like Maine in this map right here. Maine has just one neighbor. So if Maine has one neighbor, we are not reducing this alpha squared at all. So we are allowing for great uncertainty in the latent spatial effect for Maine. Much more uncertainty than that of Wyoming. You saw Wyoming has 6 neighbors. And so when we are making our spatial effect for Wyoming, we take the average of its 6 neighbors, multiply by the smoothing parameter, and then for the variance, we take alpha squared divided by 6. For Maine, we look at New Hampshire, its only neighbor. There's no sum there because it's the only neighbor. We divide it by 1, its only neighbor. We multiply it by the smoothing parameter, and the variance is alpha squared. And then we take the spatial effect for Maine from that normal distribution. So when a region has few neighbors, we allow greater deviation. From its neighbors. We allow Maine and New Hampshire to be fairly different on the count of that variance. And that's fair, that's fair. You know, if we have 6 neighbors, we have a pretty good idea of what's going on in between, right? Wyoming has 6 neighbors. We probably have a better idea of what's going on in Wyoming than we do, than the New Hampshire has about Maine, and vice versa. But it's not vice versa, because New Hampshire has more than one neighbor, right? Maine has one neighbor, but New Hampshire has Vermont and Massachusetts on the bottom as well as Maine. So for us to generate a spatial latent effect for New Hampshire with its 3 neighbors, would be taking the average of those 3 neighbors, multiplying it by the smoothing parameter, and then putting that into the mean of a normal distribution. For the variance, taking our spatial variance, dividing it by 3. So regions that have few neighbors, we are allowing for greater deviation than regions that have more neighbors. As relatively intuitive and relatively straightforward this is, this unfortunately is, oh, we're not there yet, excuse me. So this spatial smoothing parameter can be interpreted to some degree of success. If this row is almost 0, we have independent data. Dependent, not correlated. If row is 0, it doesn't matter what the neighbor's average is. We're not incorporating the information from our neighborhood into the mean of the model because we're multiplied by 0 in that case, right? So if rho is estimated to be 0, we are saying we have no spatial correlation in the model. For rho somewhere between 0 and 1, closer to 1, more spatial correlation. That's intuitive. We like that. And for a row of exactly 1, that's actually a special case of this model. And for a row of exactly 1, we actually get a new model that we won't be talking about this time, but you might see in the literature, called the intrinsic CAR. So unfortunately, this row parameter is okay to interpret as long as you don't interpret it as an autocorrelation, correlation parameter. This is not the version of the model that is available to us. It's available in that Bayesian package, but it's not available to us in our frequentist package. In our frequentist package, we have a less common variation of the same model. And it's one that instead of that diagonal matrix with a number of neighbors on a diagonal, we have an identity matrix. So instead of the number of neighbors on a diagonal, it has ones on a diagonal. This implies this conditional distribution. And you can imagine this divided by 1, divided by 1. So the conditional mean is now the weighted sum of spatial effects of the neighbors. And it too is weighted by a smoothing parameter called rho, but it's now a different smoothing parameter. It's not going to happen. Different smoothing parameter, right? Because we don't have an n in that equation. So it has to be a different smoothing parameter. It's weighting not an average, now it's weighting a sum. So it has to be a different smoothing parameter than that of the proper CAR model. The interpretation of this smoothing parameter, the one that weighs the sum of the spatial effects of the neighbors, becomes less intuitive, unfortunately. And we'll go through that in just a second. And the variability no longer depends on the number of neighbors. I don't like that because I like that the number of neighbors informs how uncertain our estimate is. And in fact, the more neighbors I have, the more connections I have, the more certainty I have about my latent spatial effect. But the model that we have available doesn't allow for that. But you can see that it's more conservative, right? It induces a greater variability because it doesn't divide by a positive number. It just divides by 1. So I don't like the fact that it doesn't allow for that variability to decrease as the number of neighbors increases, but I think it's still okay. There is a complexity here because our variance covariance matrix must be what is called positive definite in order to be a real variance covariance parameter. It goes into a multivariate normal, it must be positive definite. In other words, we must avoid exact linear combinations of the columns. And if we write our variance covariance matrix this way, apparently there is a small range of rows for which that matrix is positive definite. There's only a small range of rows for which that this entire matrix is positive definite and therefore valid to be used inside of a multivariate normal distribution. So, by the way, an eigenvalue of 0 indicates that a column is linearly dependent on other columns. So we really want to avoid eigenvalues of 0. The range that rho must fall into is the interval between 1 over the smallest eigenvalue and 1 over the largest eigenvalue of the spatial adjacency matrix. Let me repeat. Our entire variance covariance matrix must be positive definite. If it's not positive definite, we can't use it as a variance covariance matrix. There is a small range of values for which our spatial smoothing parameter rho has to be inside in order for that to work. That interval is 1 over the smallest eigenvalue to 1 over the largest eigenvalue. Which eigenvalue of what? Eigenvalue of our adjacency matrix. So what this means is that the magnitude of rho is hard to interpret. I'll say nonsensical. I'll just say it. The magnitude of rho is nonsense. You know, it's somewhere between these ratios of eigenvalues. Now, larger is still indicative of greater spatial correlation. I'm about to show you why. So before we despair entirely and you just log off and say, well, why are you teaching me this? It's completely useless. Let's try and generate some data to get a sense for how this thing behaves. So here I'm using the 64 counties in the great state of Colorado, where I live. All this code is familiar to you guys. I'm pulling off just the state of Colorado, just the counties in the state of Colorado, making a queen adjacency matrix. Yeah, making a queen adjacency matrix. Here I'm plotting what it looks like. It's 64 by 64, zeros on the diagonal, because each county is not their own neighbor. And of course, it's a binary matrix, so I have zeros and ones there. Just what we just learned on the last slide. For my conditional autoregressive model to work, my spatial smoothing parameter rho must be between negative 0.327 and positive 0.168. 0 is one of the values for which it works. You can take a look that if I put 0 into my model, I just get an independent normal. So 0 is definitely a value for which our spatial model will work. And in fact, a row of 0 indicates there is no spatial correlation, right? A row of 0 indicates that the value of our neighbors have no influence of the value of our region. So a value of 0 is definitely still interpretable. So that not all hope is lost. So what I will be doing is I'll be generating data, synthetic data. I will set my alpha squared to be 2. And I'm going to change that row and take a look at what my correlation matrix looks like, variance covariance matrix, correlation matrix looks like. And I will just visualize what the spatial effects look like. And I will take a look at what is the degree of spatial correlation induced by that row. So here I'm setting rho at 0. Right here, I have rho equals to 0. Here is the sigma of the CAR model. And I'm just plotting what that looks like. All the off-diagonal terms are equal to 0. So we have independence. So a row of 0 is still interpretable with our less convenient alternative. When I generate spatial effects with that variance covariance matrix, I get something that looks like this. And with our naked eye, I can start to pick out patterns. I can say, well, that might look like it's positively correlated. Well, the Morenzai statistic says otherwise. Right? My I statistic is only negative 0.08. My p-value is 0.8. So there is no spatial correlation. So a row of 0 really does produce no spatial correlation at all. Okay, we're happy about that. All right, let me set rho at a positive number. Now remember, I set it here at 0.165. Remember I said that the magnitude of rho is virtually uninterpretable because it has to be in this weird space. I got it right up there. It can only be as large as 0.168 for that matrix to remain positive definite. And I got it up to 0.165. All right, so intuitively, we should expect positive spatial correlation. Well, and we get some. It's moderate at best. We are almost up to the maximum. We're only 0.003 away from the maximum. I don't know, maybe the average is somewhere in this blue, right? Maybe the average is around at a clip of 0.4. So, okay, can I increase it some more? Oh, and this is what comes out with a row of 0.165. Clearly, there's a spatial cluster here, spatial cluster here, and I can verify with a Morenzai now that p-value is 0, that Morenzai statistic is large. Yes, there is positive spatial correlation. So positive values of rho do in fact induce positive spatial dependence, but they just don't behave quite on the scale that we're used to. Can I take it further? Look, I increased it by a teeny tiny bit. I think I rounded it on the slide, right? Now, look at how sensitive that is. I increased it by 0.003. And my variance covariance matrix went from that, where blue is the most common color, to that, where red is the most common color, where now I'm correlated definitely at a clip of like 0.8. Still positive spatial dependence. That Morenzai statistic didn't budge though. With 0.165, Morenzai was 0.56, so neighbors shared about 56% of the information. With the largest possible rho value, neighbors now share about 60% of the information. Any higher than this, I will be inducing linear dependence between columns. My variance covariance matrix will stop being positive definite, and I will not be able to use it. The multivariate normal distribution does not work then. What about a negative number? What about a negative number? Well, let's just kind of cut to the chase and set it to about the smallest it can be. By setting it to be the smallest it can be, I actually did manage to get that Morenzai statistic to a negative number. And for some reason, it returns this p-value. I suspect because this is a one-sided p-value. So I apologize for that. But if you take a look at what that Morenzai statistic is and what that variance is, we really should have rejected that as evidence of negative spatial correlation. This map is apparently evidence of strong negative spatial correlation. But we see that when we look at the variance covariance correlation matrix, that there's still a lot of correlations that are positive. Yeah, there are some that are negative. The blue colors are now negative, but the yellows and reds are still positive. So in short, be very careful if you start to look at the magnitude of your spatial smoothing parameter. A value of 0 still very much indicates that you have spatial independence. A positive value tends to indicate positive spatial dependence. A negative value tends to indicate negative spatial dependence. But as far as interpreting the number itself, good luck. Good luck. Let's go through a nice and relatively straightforward example, and we'll end it there. We will go back to my hometown of New York, and we will look at gonorrhea. We've looked at it in previous lectures, so I'll continue looking at that now. The gonorrhea variable is already a rate. And so we don't need a GLM. That's why I want to look at this first. We don't need a Poisson. We don't need a negative binomial. We don't need a binomial. It's already a rate per 100,000. So there's also no need for a population at risk offset term. I came up with a working hypothesis. I think that, and I think this is at least a 2-beer hypothesis, guys. Now I'm trying to, of course, illustrate a model, not write a public health paper. But I think this is a reasonable hypothesis that gonorrhea rates are driven by having an area having an active nightlife. Now, notice, I'm not making any statements about individuals. I don't have data at the scale of individual. In New York City, I have data only at the scale of neighborhood. Now, these are still far smaller than county, but I cannot make any statements about the individual. And so there is something called ecological fallacy. So just ecological fallacy. We cannot assign the characteristics of an area, no matter how small, even a block group. We can't assign the characteristics of an area to an individual person. So I'm not saying that the gonorrhea risk for an individual will be higher if they are going out every day. Doesn't sound completely unreasonable, but that is not what these models are trying to do. What I'm saying is that the gonorrhea risk in an area is driven by having an active nightlife, maybe a lot of restaurants, nightclubs, hookah bars, I don't know, when adjusted for relative covariance. Now, active nightlife is difficult to measure. Am I counting, what am I counting? Am I counting bars? There are all kinds of different bars, right? There are Irish pubs, and then there are sort of dance clubs. Which ones are contributing to gonorrhea? I have no idea. I have no idea. Active nightlife is difficult to measure, but this seems exactly like the job for our latent spatial effects. These latent spatial effects, I hope, will sort of act as a catch-all for everything important that is not noise, that is spatially structured, that is not in the model. So I'm hoping that our spatial effects will reflect the presence of active nightlife, broadly defined. So here are my relevant covariates, and I too am bounded by the data set. It's that publicly accessible data set that I got. Borough is a simple one. Bronx, Brooklyn, Manhattan, Queens, or Staten Island. Median rent I'm including because I think higher rent areas might have more nightlife amenities. That makes sense. You know, people tend to live a little bit more to be around restaurants and clubs, etc. And now I'm including the population who do the nightlife. And I definitely, when I first wrote this, I stopped at 18 to 24. That's most of you guys. But that doesn't include me. And I like to think that I'm still a person who does the nightlife. And so I was like, yeah, let's go ahead and add the next group in there. That goes up to 44. You guys go. That's right. We've got to be partying at 44. Now, all jokes aside, not only are 18 to 44-year-olds probably more likely to be active in the nightlife. If you look up gonorrhea statistics, these are also the age groups that are high for gonorrhea. Now, that's a definition of a correlation and not a causation, but it makes a ton of sense for me to include percentage of the population, 18 to 24, your college-aged population. And then the next one, let's call them young adults. Pat myself on the back. Young adults. Young, let's write it down, man. If you don't write it down, it doesn't happen. Young adults. Young at heart. I'm 35, right in the middle of that range. So a reasonable first step might be to plot my outcome variable, which is the gonorrhea rates, and look at the maps of the three things I'm trying to use as covariates. The boroughs are visible here, right? The boroughs are, here's Staten Island, here is Brooklyn, Queens, Manhattan, and Bronx. I'm less interested in tracking the boroughs, but those are just so easy to account for that why not? I'm looking at how the high areas of gonorrhea are matching up with my potential covariates. And it's super interesting because it looks like areas where rent is low, for example, right there, kind of corresponds with an area of high gonorrhea. But in Manhattan, we have high rent and there's also high gonorrhea. So it's not an easy one-to-one relationship. It looks like it might vary by borough. We look at population 18 to 24. So population 18 to 24 actually doesn't look like it has a strong spatial dependence. It looks a little checkerboardy. But what's interesting is it's pretty clear that population 25 to 44 is concentrated in similar areas to the where gonorrhea tends to be rampant. So I'm expecting that positive association with this variable, and I really don't know. I really don't know how median rent and population 18 to 24 will correlate when we all adjust for things together, including a spatial latent effect on the scale of neighborhood, how that will be associated with the gonorrhea rates. Okay, I'm taking the natural log of the gonorrhea rates. Again, these are rates per 100,000 people. I have a normal distribution. I'm including my spatial effects into the mean. And then on this scale, this is just independent. What I'm saying is, once I account for my spatially structured latent effects, what is left over is random noise. And I'm comfortable with that. This is that conditional way of specifying a normal spatial model. Now remember, the rho parameter that we'll be estimating has to be between 1 over the smallest eigenvalue and 1 over the largest eigenvalue. So this is the range of values for my adjacency matrix that rho can be. So a rho of 0.5 is impossible. A rho of negative 0.5 is impossible. A rho of 0.18 is going to be considered large. We're coming up to almost the maximum possible, right? So this type of analysis can help judge the magnitude of rho, but I really think you shouldn't. I just think that's just so much trouble there. Let's fit our model. We are going to be using the SBAMM package. The code is fairly self-explanatory here. The key is to make sure that your data are ordered by the identifier, the unique identifier for each region. Then you put together your adjacency matrix. Make sure it's symmetric. It has to be symmetric in order to be included inside the variance covariance matrix. In this case, it's 181 by 181, and then we fit the model. Let me flip into R. Whoops, that's not R. This is R. All right. Oops. I'm pressing all kinds of things, and I apologize, guys. All right, here I'm putting together the adjacency matrix. If I want to visualize what that looks like, I can run this image command, and it will output the ones and the zeros inside of that adjacency matrix, right? Only two values, ones and zeros. Ones when the neighborhoods are touching, zeros when they're not. I'm going to ask if my matrix is symmetric, and it is, and that's apparent. And its dimension is 181 over 181 as promised. Now, this SBAMM package is a newer package for spatial analysis, and it's the only one that I'm super familiar with that allows us to fit a conditional autoregressive model. Now, you will notice the code is very intuitive, right? This is just an regular R model, log gonorrhea. Here is the borough, median rent, centered and scaled, percent population 18 to 24, centered and scaled, percent population 25 to 44, centered and scaled. Here we get spatial. Adjacency, 1 vertical bar NTA code. We tell the R package that we have specified our adjacency using NTA codes as unique identifiers for each area. We have to provide our adjacency matrix to the model. We're going to be using ML. This is maximum likelihood. We are familiar with maximum likelihood. You guys have coded maximum likelihood by hand, so there are no excuses. And we run the model. And this runs quite quickly. It gives us our output that will match what I have on the slide. So the reference group is the Bronx. R takes alphabetically, the first level alphabetically to be the reference group. So it looks like Brooklyn has a lower gonorrhea rate than the Bronx. Manhattan has not significantly different gonorrhea rate than the Bronx, and Queens and Staten Island are both lower in terms of their gonorrhea. Good for them. Median rent, when we adjust for age and the spatial effects, it looks like I was wrong about median rent. Or it's rather that areas where median rent is high tend to have lower gonorrhea rates. I thought that median rent might be associated with having places to do the nightlife activities. That might not be the case, because after I adjusted for everything in the model, the coefficient of median rent is negative. Here are my two age groups. And as expected, they're both positive associations. The more 18 to 24-year-olds, the higher the gonorrhea rates, but the association is far greater. Look at this test statistic. It's 9.7. It is by far, not by far, it is the most important covariate outside of the intercept in the model. So it looks like areas with 25 to 44-year-olds tend to have higher rates of gonorrhea. Here is my row term. All of my cautionary tales about interpreting its magnitude come to mind. I have no idea what the 0.18 means, but I'm going to go back to this slide and show you that it can be only as large as 0.183. It can be only as large as 0.183. We have estimated 0.182. So it's quite large, actually. The degree of spatial dependence of the latent spatial effects. And this, again, is everything that is not in the model that is spatially structured is quite strong. We should always test our models in terms of the residuals. So you can see I'm using a QQ plot of the residuals of my model. And this looks about as good as you will ever see. My God, if I had this kind of QQ plot for every model I fit, I would be a happy person. This looks like, at least on this particular metric, there were no assumptions violated. The residuals are looking to be white noise, at least normally distributed with mean zero. I can extract and plot those latent spatial effects and examine my hypothesis that areas with active nightlife are being picked up, that my nightlife activity is being picked up by these spatial latent effects. So you see that I just grabbed them as ran F from from my model, and this just makes it easy to grab. It's just the first one in the list. I attach them into my original data set. I'm actually going to make my map interactive so I can zoom in and look at things, and then plot. You can see I'm using a divergent palette, only 5 levels. I'm just really trying to hone in on my hypothesis. Okay, from this scale, it already looks like there was some interesting stuff going on. For example, take a look at the west side of Manhattan versus the east side of Manhattan. Looks like the entire west side of Manhattan is elevated in terms of their spatial latent effects. There's something there that our model is not picking up that is indicating more gonorrhea on the west side of Manhattan than on the east side of Manhattan, and also in West Village, in Soho, Tribeca. So at first glance, I think my hypothesis is kind of falling apart, because if you were going to go out in New York, you can go out in Chinatown, you can go out in Soho, Little Italy, you can go out in the West Village. I rarely personally go out on the Upper West Side. That's a relatively wealthy area up there. So if we zoom in a little bit, I'm going to change my my map. You can sort of see about what kind of region we're picking up. In short, I think my hypothesis is mostly fallen apart, because the vast majority, at least in Manhattan, of places to go out are here, below 14th Street. It's not to say there are no bars or restaurants on the west side of Manhattan, but that is not typically what you would consider a place to go out. So our spatial latent effects are definitely picking up something. They're definitely useful, but what they're picking up, maybe they're picking up wealth, right? I do not have income or wealth in the model. That could be picking up wealth. That's a reasonable statement, but as soon as I said it, why is it not picking up wealth on the east side of Manhattan? On the east side of Manhattan here, there's a lot of wealth as well, but it's very clearly delineating west side of Manhattan, east side of Manhattan. Apparently something pretty remarkable happens when you cross Central Park. When we move into Brooklyn, we see that there are some elevated areas with elevated risk, more gonorrhea there that is spatially structured, not noise, and is not picked up by the model. Right over here, it's a kind of a young, hip area, but Williamsburg is yellow, right? It's that there's nothing really happening. There's no elevation relative to what our model already accounts for. But Dumbo, which, by the way, a little trivia for you guys, Dumbo stands for down under the Manhattan Bridge overpass. Manhattan Bridge is right here. There is an overpass, and there's a little park. If you're ever in New York, come eat there. There's a beautiful view of the skyline. But Dumbo is has an latent effect estimate, 1.36. That's on the logarithmic scale. So it looks like the risk for gonorrhea is elevated there at a clip of 3.9 times. 3.9 times higher risk for gonorrhea in Dumbo. And that is kind of an area where there's a lot of restaurants, a lot of nightlife. So maybe to be gentle with myself, I will call my hypothesis to be partially supported, but maybe not as strong as one would hope. It is interesting that the areas around JFK here are a little higher elevated. Where I grew up looks to be slightly elevated in terms of the gonorrhea. So we are calling this as partially supported, but not particularly strong. The latent effects are picking up something else. I'm sure you guys will let me know if you come up with a more plausible explanation. So this is definitely what is done, is you fit a model that is reasonable, that is in pursuit of a hypothesis. You determine whether the latent effects are necessary. And for us, the value of this rho is definitely large enough. It's almost at the maximum, right? We saw with those variance covariance matrices that we're inducing a lot of positive correlation there. And now we can sort of take a look. Are there interpretable patterns that are being reflected by our latent effects? Here, the patterns I thought would be reflected are mostly not. And so my hypothesis crumbles to the ground. We have one more example to go through. We will do that early next week. Thank you guys for your attention. Stay safe and be well. Thank you guys. Goodbye.